Our next speaker is Mr. Ted Dowey. Ted Dowey's from the New York City DEP. He's spent his career with the DEP, and he's going to come talk to us about the history of the Delaware Aqueduct, moving out of transit into the water system for New York City. So, Ted?
I'd like to thank the organizers of the Fox Conference for giving me the opportunity to talk a little bit about the history of the Delaware Aqueduct. We'll take a sort of illustrated look at the work that they did back then, and then I'll bring us to the present with a video that we have. You may know that the Delaware Aqueduct, in particular the Randolph West Branch Tunnel, is leaking, and we have a recent video of the actual leak from the inside. Most of the information that I'm presenting is from old Board of Water Supply reports, but any of you are interested in the New York City water supply system, Diane Galusha's book, Liquid Assets, is also very interesting. New York City has, maybe the greatest water supply system in the world. When the reservoirs are full, we have over a year's supply of water. We're using about 1.1 billion gallons a day. That water is used by 8 million city residents and 1 million upstate residents, and all that water flows to the city by gravity. So just briefly today, we'll just touch briefly on what the New York City water system looks like, and then rather than covering the entire Delaware system, I figured we'd really need to sort of zoom in on the construction and one part of the Randolph West Branch Tunnel. I think it would be a little more interesting to have more photographs rather than trying to cover decades of construction. Then we'll take a quick look at the inspections they did of that tunnel in 1949 and 1957. This tunnel is now leaking. You heard it mentioned this morning that it's leaking somewhere on the order of 22 million gallons a day. So these leaks developed in the 90s, and we have some inspections to report in on at the end of the talk. So New York City water system is here. Here's New York City down here. This is the Croton system. Croton system was put in service in 1842. Excuse me. The Croton system provides the city with about 10% of its water. The Croton system was put in service in 1842, but work continued on the Croton system until 1911. The Catskill system was the next system put in service. Work started on the Catskill system in 1907. The Catskill City can provide the city with 40% of its water. Work started on the Ashokian Reservoir in 1908. It's located up here, and then ultimately in the Schoharie Reservoir in 1919. The water is brought to the city through the Catskill Aqueduct. The Catskill Aqueduct consists of 55 miles of cut and cover tunnel, 14 miles of grade tunnel, 17 miles of pressure tunnel, 6 miles of steel siphon. Part of the Catskill system also was the construction of Kensico Reservoir in Westchester and Hillview Reservoir just north of the city. And then that part of the Catskill system was the distribution of the water throughout the city through City Tunnel Number 1. So as early as the early 1920s, it became evident that the demand for water in New York City was going to outstrip the supply of even those two systems. The predictions were that by 1932 we'd be in trouble. So the Board of Water Supply started looking for additional sources of water. Initially, they looked at additional sources east of the Hudson, but they found that that was not going to work. So they started looking to sites for reservoirs and tunnels west of the Hudson. By 1927, these sites for reservoirs and tunnels had been located, and by 1932, they were ready to go out to bid. However, the city's financial condition related to the Depression caused a postponement, and it wasn't until 1936 that $17 million was approved and the Delaware system construction started. Initially, there were contracts for 31 shafts associated with the tunnels that were comprising the Delaware system. So the Delaware system initially was the Randolph Reservoir located here, the Randolph West Branch Tunnel, which was 45 miles long, the West Branch Kensico Tunnel, which is 23 miles long, the Kensico Hillview Tunnel, which is 13 miles long, and Randolph Reservoir. The Delaware system continued to be developed with the addition of Neversink, Papacton, and Cannonsville reservoirs out here, and that system now provides the city with 50% of its water. There was a Supreme Court decision because these reservoirs out here to the west take water that goes into the Delaware River and the Delaware watershed. So there was a Supreme Court decision which arbitrated how much water New York City could take back into its water supply system. We've heard a lot about the human cost of building or doing all this work. So I just wanted to touch base on some of this. In 1911, I was reading some of the old reports, there were 17,000, this was an unusual year, there were 17,000 people working on the New York City water supply system that year, and there were 98 fatalities. In the Catskill system, there were 427 deaths associated with the construction of the Catskill system, and numerous other accidents. So for the Delaware system, there did seem to be a somewhat concerted effort to reduce the number of the human cost for all this construction. And indeed, in 10 years of construction, 79 people died in the construction of the Delaware system, which was certainly not acceptable, but certainly a lot better. There were also some laws passed by New York State addressing the conditions of work, in particular silicosis, and these laws of 1937 required the use of water during drilling and required the use of introduction of ventilation into the shafts and the tunnel. And as an aside, some of the Delaware system was constructed during the portions of World War II. 277 workers for the contractor and BWS went into the service, and 8 died while serving our country. So the Delaware system was a little bit different from some of the other systems, as that there were no work camps maintained. People lived in the neighboring areas and drove to the work sites. The tunnel equipment was getting a little bit better, and we'll show you some pictures of some drill jumbos and some track-mounted mucking machines. Much of the work of the Delaware system was done by 1941, but again, the war impacted the final construction. There was competition for metals and primarily mechanical components that, the war needed the steel or the metal so that procuring the valves became a problem, for example. So the war took its toll on the completion of the Randolph West Branch Tunnel in particular. The Randolph West Branch Tunnel was activated in 1944. The city must have really needed the water. They diverted Rongerat Creek into Shaft 1, and it supplied an irregular source of water for a period of 3 years. I keep trying to envision what permit it is you get in order to divert a river into your shaft, but I haven't been able to determine what that is. So we're going to take a look at the Randolph West Branch Tunnel. The Randolph West Branch Tunnel is a 45-mile-long tunnel. This is a cross-section of it. You see the Randolph Reservoir on the left and West Branch Reservoir on the right. The 2 green spots are where we have leaks presently. But I thought we'd focus on the construction of the Randolph West Branch Tunnel in this area right beneath the Hudson River. It's a deep rock pressure tunnel. It's 13.5 feet in diameter. It's 45 miles long, and under the Hudson, it's 600 feet underneath the Hudson, which is part of the problems we have. So in 1937, March of 1937, Contract 333 was put out for 4 shafts. There were 8 bidders. The winning bidder was Fraser Davis. They came in with a bid of just under $2.3 million, and they were going to build these 4 shafts, and each of the 4 shafts had 200 feet of heading in each direction. So this is what some of the shaft sites look like, and we're building 2 shafts presently in order to fix the leaks, and it's surprisingly, we're running into the exact same problems now that we ran in there. And one of the things you had to do is bring power to the site, so literally CHG&E was in business then and is in business now. Brought power to the site, powered the hoists and powered the pumps. You see a steam-driven crane on the site as well. The initial 100 feet or so of the shaft was sunk with the steam-driven crane, but the horsepower of these cranes was somewhat limited. I saw one of them rated at about 45 horsepower. So I think that that was the reason for switching over to this sort of hoisting system. There were compressors on the sites, and but there was no water, so the laws mandated you needed to use water in construction, so a lot of the construction sites had to sink their own wells. This is actually slightly in the wrong place. This is a hoist house associated with the tunnel a little bit later on, but you get a sense of what the hoist house looks like. This massive 500 horsepower electric motor, a gear reducer here, and a massive drum here. And this particular hoist ran a sizable 12 cubic yard skip. but that gives you a sense of what the hoist capabilities look like. This is one of the larger ones. This is actually one of the shafts by the Hudson River. Now, you know, if superficially this looks a lot like the head frames we use now in sinking our shafts, but the head frames we use now are strictly for the personnel cage, and they have safety ropes and guide ropes, and they're dedicated to personnel. This thing handled everything. This bucket here handled the muck. When the men came out, the men got in the bucket. When the muck needed to get dumped, they pulled the bucket over to the side and it would dump into the hopper. If there were men, they'd pull it over to a different side and drop it down and you'd get out. So, you know, it may look safe, but it's not really all that safe. It's just one line running through a head frame. The drilling that was done, they used 55 and 90-pound Ingersoll Rand drills. The powder was supplied by Hercules Powder in 50-pound boxes. There was a ventilation system providing about 3,000 CFM to these shafts. And one of the reports, BWS reports, notes the use of safety helmets, which are newly required. And they say, quote, "These helmets have demonstrated their worth in several instances, and a few instances have undoubtedly saved lives." So you will see some pictures of some people wearing some safety helmets. This is another one of the shafts. Again, here you can see the truck parked under where the muck skip dumps, your steam crane, and shaft forms. The shafts were excavated, and they excavated about 40 feet out, and then they turned around and set these 5-foot-high forms and concreted themselves back up. And the turnaround time for concreting a 40-foot section was, you know, just a matter of days, somewhere on the order of 3 or 4 days. So it was very efficient. These shafts were operated 24 hours a day, 5 days a week. Let me jump ahead to this slide. This was the concrete batch plant that fed the 4 shafts, and 3 of the shafts were on the west side of the Hudson, and 1 was on the east side of the Hudson. So here you have the aggregates here. The aggregates were all mixed and weighed and put into the trucks, which you see on the right-hand side, and these trucks then took the aggregates to the shafts where they added water, and I'm not entirely clear where they put the cement in, whether it was initially put in, but they were mixer trucks, so it was a little bit of a mystery to me. But what happened was on the eastern shaft, the truck had to get on a ferry, and the ferry had to go across the river. There was no Interstate 84 bridge. So the contractor in that case built a little concrete plant right next to the shaft. And here you can see there was place for aggregates to put in. Here's a little mixing drum, and this is literally a 1 cubic yard trolley, which then gets put across over here and dumped into the muck bucket, into the concrete bucket. Concrete bucket would be lowered down into the shaft, and the concrete would be placed behind the forms. There's a picture from the head frame looking straight down one of the shafts. And again, this is that heading at the bottom of the shaft, and you're actually standing at the heading looking back at the shaft. See a bunch of guys in rain gear appear to be mucking by hand at the base of the shaft with a sort of bucket in the middle here. As you can see, there's no rock support. There were no rock bolts in those days, and we'll get into a little bit later what's involved with supporting the rock. These shafts made tremendous progress. Shaft 5A, which you see in the middle here, went from plus 400 to minus 500, over 900 foot deep shafts, and these shafts were all completed in about 2 years. The shaft contracts came out in 37, and the tunnel contracts that followed up came out in 39. So this was the contract that was for the tunnel in the same area. This was for the tunnel that was going to be driven from shaft 5A and from shaft 6. It was awarded to Pleasantville contractors for $10 million. It was over 36,000 feet of shaft. There was a head frame made by American Bridge and skips by Union Ironworks. There were 2 different rates of speeds that these skips traveled, but they went between 400 and 600 feet per minute. And the shaft hoist, which you saw earlier in the picture, was that 500 horsepower motor, and it didn't appear to have a 9-foot diameter drum in that one, but maybe that was the slower hoist. We'll talk about progress in a little bit, and I'll show you some pictures of the ground support that was used at the time. But mucking was done with a 75 horsepower mucker. They mucked into 5 cubic yard muck cards. They had a rail system, 36-inch gauge rail on 60-pound rail, and the cycle time was 6 hours and 30 minutes. In the tunnel, they actually worked 24 hours a day, 6 days a week. So here's some photographs associated with the tunnel construction. This was the air compressor house, and this vent line went all the way down the shaft, and then they had a 26-inch fan line that went down into the tunnel. I'm just going to skip this ground support system. This is one of the drill jumbos. This is a 36-foot long drill jumbo. It's got drills in various locations, and obviously, as you know, you take the drill jumbo up to the face, you drill your holes, you pull it back for the blast, and then the mucking machine and the muck cars are passed through the middle of the drill jumbo. This one had a very sort of novel way of dealing with how you cycle the muck cars around behind the mucking machine. And if you look closely, you see the wheels of the muck car, which is elevated by this drill jumbo. So they actually picked the muck car up and drove the train back and forth underneath them, as opposed to, there was a neighboring contractor that used a California switch to cycle the muck cars around. Those are the wheels of the muck car. Presumably you pick up the empty one. This is the drill jumbo next door, the neighboring contract, completely different look. But it must have had to be pulled back on the California switch and fold these decks in. And as you can see, again, there's not a whole lot of rock support going on here, and that's because this is the drawing of what the rock support looks like. There was structural steel members, which would be either founded on posts or a piece of rock or a wooden post to hold up the rock. And as you can see, it wasn't a trivial exercise. This is the Conway mucker. This machine, this guy here is the operator. You just lay this bucket down and move the whole machine forward, and the bucket would fill up with muck, and you tip it over backwards, and it dumps onto the conveyor belt. And then you can take it to the shaft. Here's the shaft here, and you can see one of the muck cars dumping in this section. It appears that they're built to be dumped on either side. Again, here you can see the rock support in the vicinity of the shaft. And what might look like rock bolts is actually drill steel. So all the drill steel was sharpened and continuously remade by blacksmith shops up on the surface. And that's when a nipper was really a nipper. His job was to cycle the drill steel back and forth. The tunnel was serviced by 10-ton General Electric locomotives. There were 2 DC motors on this thing. And when the headings got too far away from the construction shaft, they actually put it in an overhead trolley line so it didn't burn the batteries quite so much. It was a very labor-intensive operation. This was the day shift for 2 headings. I counted up 107 people associated with these 2 headings. At one heading alone, there were some additional people. You had 6 drillers and 6 drillers' helpers and 10 laborers. So there were a lot of people involved with this construction. Progress was phenomenal. This was, again, a 13.5-foot finished tunnel. Here you see the construction shafts in here, and they're averaging 265 feet a week, and that's over 12,000 feet. So progress was really substantial, and this is excavation alone. One of the problem areas was 6 North here. They have a substantially lower area, lower progress rate, and we'll take a quick look at that in a minute. Surveying was also a challenge. Here is a surveying from 2 directions between 2 shafts, a distance of 27,000 feet, well over 5 miles, and the difference in grade when they met was substantially less than an inch. So that's pretty impressive. Not quite so well done in the alignment. Here's a 15,000-foot section of tunnel between shaft 5A and shaft 6, and the alignment was off by 1.8 feet. I don't usually mention it, but I'm secretly glad I work in water tunnels because, the water will go wherever you need it to go. As long as we stay within the easement, if there's a little bit of an alignment issue, we're good. In 1939, that shaft 6 north heading drilled a test hole at station 1521 and resulted in 700 gallons per minute coming through this small hole. It also washed out a total of 25 cubic yards of decayed rock and 20 cubic yards of what they called sand. And the pressure was also substantial at 240 psi. So they realized they had a problem. So what they did is they came in and did some diamond drilling and poured in 4 diamond drill cores out ahead of the heading. The depths were between 141 and 300 feet. These holes themselves also were producing an additional 1,600 GPM. So presumably while that was going on, they built a bulkhead back from the area that was problematic, because if you ended up, getting more water into the tunnel than you could pump, you could really lose this whole portion of the tunnel. So they put in a 20-foot thick bulkhead. And then it took time to actually mine through that area. So these are three different visions of the tunnel. There's a center line here, a center line here, and a center line on the far side, on the right-hand side. And what they decided to do to get through this bad area is to put in two drifts on the bottom left and the bottom right of the tunnel. And this was a 7-foot wide by 8-foot high drift. They drilled and blasted. They stood timber sets every 5 feet. They initially were mucking by hand into wheelbarrows, but once they got in a substantial way, they managed to fit in a muck car, which was 2/3 of a cubic yard, and they put that on a 24-inch gauge rail. And these headings went in 215 feet before they found good rock on the other side. And talk about, this was an area where there's huge amounts of water, bad rock, and water under substantial pressure. So somebody was earning their living every day going into those two holes and building that section of the tunnel. Ultimately, what happened was that was mined successfully, and was this area is the area where the drift was, and they put drains in here, so the water, when they came back to mine through the entire face, there was a drain on each side of the tunnel, which was initially done by this adit. So then they were able to go through and mine. They had planned to have 2 additional adits, but they found out that they could actually mine the rest of the thing all in one face. But they did stand what they did for rock support there, the structural steel, which looks like this. And they also recognized that this would have to have a steel interliner in it in this particular section. So they decided on 1,100 feet of steel interliner. It was 1 inch thick. It was 16 feet and 4 inches in diameter. So you could put the steel interliner in and then put a reinforced concrete lining on the inside of the steel interliner as well. So they needed to assemble this steel interliner to some degree down in the tunnel. So this was a chamber that was down in the tunnel. It was where the interliner was actually riveted together. So this is the sort of pre-invert that they had, and they built a structural for those twisted rebars, which were in fashion at the time. And so they had some structural steel outside the outside the steel interliner. And then they put the steel interliner inside that, assembled that in sections, and then a reinforced concrete lining was placed inside this. We think that one of the reasons we have a substantial leak of the tunnel is that this interliner wasn't quite long enough. It was about 1,100 feet long, and we think it's leaking around the ends. And so perhaps if it had been longer, it would have been better for us in the present. So then it comes time to concrete this tunnel. Pleasantville contractors had a sort of unique way. The neighboring contractor actually had agitator cars, and they sort of drove the agitator cars in and then actually pumped the concrete into the invert and the arch forms. But this contractor actually they had what was called batch boxes, and these were boxes on a train, and they dropped the aggregate down into these batch boxes, and they got cement somehow into the other one, and so 2 batch boxes formed a mix. And these were driven into the tunnel. Here's a California switch over here into the sort of gantry system, which was then, these batch boxes were dumped one by one into this mixer over here, which would then dump into the pump, and the pump would then pump the concrete out the far end. And this is the setup for the invert, but I'm told that the report said that they used the same setup for the arch in this particular section of the tunnel. You'll see it says an operator up here running this sort of thing. So here's this guy up here running this thing and picking up these batch boxes and dumping them into the mixer. And the mixer's on the far side here. This is the pump, and the concrete is being pumped out. And in this case, it's going into the invert. Here you see a nice clean invert. They had poured previously concrete curbs at the correct grade, line and grade along the side. There's a board here for making the radial joint, and that's how there was a screed in the far end, and they would progress that. That's how they set up pouring the invert. Like I said, I couldn't find a picture of the arch forms for this contractor, but I believe the arch forms are actually similar on the adjacent contract, and here's the existing invert, and here are the arch forms, set in place, and then you have a form carrier in the middle that takes the forms from the back and brings them to the front, so you can have a continuous concrete pour operation that was going 24 hours a day, 6 days a week. They did have 390 feet of tunnel forms. And to make a long story short, that's how we built the Rondout West Branch Tunnel. There was an inspection in 1949, which was a result of, I guess they were capable of shutting down the tunnel for a short period of time, and since that river had been diverted into the tunnel, I guess they wanted to take a look at what was the situation in the tunnel, and there were really no issues. The concrete was in good shape. They did find some deposits in the tunnel, but the 1949 inspection really wasn't a big deal. In 1957, they went back in the tunnel. They were having questions about the capacity of the tunnel. They were worried about the biofilm that was developing. There were some mechanical parts associated with, there's a bronze door associated with the pumping station at Shaft 6. So they were worried about that. They went in 1957. The first time they used a farm-oil tractor. In the 50s, they used a Jeep. They didn't use any ventilation either. Some of the engineers complained that the ventilation from the diesel engine really wasn't quite appropriate. But here you can see they did find some mounds of debris in the tunnel, and you can see the line here is where the mound of debris was, and presumably that came out of this grout pipe. So there were a couple of open grout pipes which they went in and they regrouted them and they mucked out the tunnel. But there was really no indication that there was a leak at that point. And at the far end of the tunnel, they actually found a whole bunch of cobbles which had evidently come 45 miles, been washed down while the tunnel was in service. So this was actually at Shaft 9. So in the 90s, the leaks were sort of discovered, and they took the form of surface expressions in Roseton. And here you can see literally a stream on the west side of the Hudson. And in the Hudson, at low tide, you can actually see water bubbling up into the Hudson. So the city got some autonomous underwater vehicles, looks like a submarine. It went the full length of the tunnel. It took a bunch of pictures, and we determined that there were really no structural gaps in the lining. The lining was all intact. We were able to enhance these photographs and create crack maps for the entire tunnel. As you know, unreinforced concrete pressure tunnels are cracked everywhere, so that's not unusual, but we were able to take the historical records, the certain areas of increased cracking, the surface expressions, and determine where we think the tunnel has been leaking. So just this past fall, and I have just two more slides here, we were able to put a remotely operated vehicle, which actually shows you live pictures and you can swim it around into the tunnel. And just wanted to show you a couple things. There are some nylon string tail tiles here, and this thing does a lot of other things, but I'm just focusing on the nylon string tail tiles, and also can inject dye out into the water. And this thing was put into the tunnel. So here it is swimming up the tunnel. It's about 3 miles up the tunnel, and this is the wall of the tunnel. There's a stick sticking out of the side of this tunnel, and sure enough, when you started poking around, all of a sudden the strings are being sucked out of the tunnel. So while the tunnel wasn't in full service, it was still pressurized, and so here you actually have a triple junction between the invert and 2 vertical concrete pours, and there's a leak. Another interesting thing is that we were actually able to take the crack maps from the AUV and follow them in the ROV, so you could actually tell where you were in the tunnel. And I don't know if it's exciting to you, but it was exciting to me. If I can get this to run, the ROV has more than just, it's able to squirt this dye into a crack here, and you can see that this tunnel is leaking actively while you're actually live and in color. And while we're not happy it's leaking, it does show that we've calibrated our crack maps, and the program is certainly headed in the right direction. So that brings us up to the present, and that's it for my presentation. Thank you.